Welcome everyone. I am absolutely delighted to be here to talk to you about our work. This is my second time speaking at AWE. I am absolutely thrilled to be back here. So I am an assistant professor, soon to be associate at Duke University. My PhD is from Columbia, my postdoc is from Princeton, and over the years I've worked in industry in the multiple roles, and I had the pleasure of being affiliated with the companies that are shown on the screen here. At Duke, I lead the Intelligent Interactive IoT Lab, which has grown to include about 10 senior researchers, PhD students, and postdocs, as well as a wide range of other researchers. We are huge believers in undergraduate research. We have high schoolers with us. If you're ever in Durham, Raleigh area in North Carolina, please look me up. I would be thrilled to show you what this delightful group of people have been up to, what kind of exciting AR apps and AI we are currently building. We work on next generation augmented reality, and specifically we work on making augmented reality context-aware and reliable. By context awareness, I mean augmented reality experiences that respond to the state of the user and the state of the environment. And by reliable, I mean reliability in a true cyber-physical sense of this word, that systems that are so reliable that you would trust them to be a part of surgery that's performed on you, or that you would trust in guiding you in working with a large and dangerous robot. We are a computer systems lab. We don't just build the end interfaces, we build platforms. So a lot of our work includes edge and cloud components, as well as external sensors and actuators. And you will see the role of specifically edge computing in next generation AR later in this talk. And at AWE, augmented reality requires no introduction. But I would like to spend just a few moments making sure that we all have the same vocabulary in mind. This work is specifically about augmented reality, meaning building virtual content in context of the real world. So our work is about this interaction of real world and virtual content. Examples of specifically augmented reality applications are on the screen there. That IKEA Place app, where you build virtual furniture in context of the world around the user, or where you take, in the Google Translate app, you take pixels in a foreign language and you replace them with pixels in the language of your choice. So it's true interaction of real and virtual. Augmented reality existed in labs since 1970s, but has reached the consumers relatively recently. Release dates for the early SDKs and earlier, specifically AR devices, are shown on the screen there. A couple of recent additions of specifically AR capabilities are capabilities of Apple Vision Pro, as well as the pass-through capabilities of Quest 3. And on the expo floor, you see a number of other devices that specifically do AR. My lab builds a wide range of AR experiences. You see at the bottom left, you see an example of a cognitive assistance app where AR is helping users solve a Sudoku puzzle. On the top, you see an example of an AR app that guides users on learning to perform CPR. It guides users on the depth and the strength and the frequency of chest compressions that are performed as part of CPR. To the middle is an app that we have been working with our partners in neurosurgery, where we are using AR to help surgeons target a specific part within the brain of the patient. And to the very right is an example of an app where AR, in this case a HoloLens, is used to visualize the information of a robot. So here you see visualized in AR the information about the intended robot trajectory. And I hope this works. If you look carefully at the video on the right, you will see that as the robot hits obstacles, the trajectory changes, and this is reflected to the user in real time within the AR interface. Out of all apps that are possible with AR, and there are a million possibilities out there, arguably the most interesting apps are those where augmented reality experience changes with the changes in the state of environment around the user. Experiences where types and locations of objects around the user are automatically identified by the AR application and the application responds to it. An example of this type of, we call this semantic scene understanding. An example of an app that relies heavily on semantic scene understanding abilities is shown on the screen there. This is not from my group, this is from a group at ETH Zurich. But I really like this example. What happens in this app is that you replace in real time selected objects in user's view, in this case cars and pedestrians, with 3D objects. So in this case, what's happening is that they are replacing the cars with these. And note that this requires a lot of ML processing, a lot of scene understanding. You have to recognize the cars. You have to find out their pose, because otherwise the B won't be angled quite right. It has to be moving in the right direction. And you have to keep tracking it. So this is very ML-heavy work, and this is scene understanding at its finest. So you might ask why this isn't there. Why do we not have AR apps like that? Well, one reason is that the type of ML that is needed for that is very resource heavy. You really cannot run it on device. And so this is where edge computing and cloud computing have become the de facto standard solutions for bringing that level of capability to AR. The other reason, though, is that up until very recently, you really could not do that with real-world AR devices in real environments. ML has been with us for a while, but up until very recently, the finest state-of-the-art ML was trained on very specific circumstances. And objects were recognized if they're positioned in a very specific way in a very specific set of environments. And you could use a model to recognize a certain set of classes, let's say 40 classes or 25 classes. This is okay if you are in some very specific environment. But for AR, this is extremely limiting. That by default, your AR system sees the world as it is. It is not restricted to seeing 40 classes of objects that your model knows. It sees all the objects. It is, you are looking at the world every which way. You are angled different ways. The lighting is different. The set of, there could be abstractions in the way. Overall, you're operating in a so-called open set condition, in a open set environment. And classical ML models, although you see their performance, them exhibit very good performance in data sets, they could not handle this open set conditions. And this is where VLMs are absolutely transformative, because VLMs are designed to work in open set environments. This is where I'm extremely enthusiastic about the future of semantic scene understanding currently. Because finally, for the very first time, with the advent of modern models, we are seeing the ability to operate in these very challenging conditions and operate in them well. So let me talk to you about one architecture that we have been building. It relies on semantic scene understanding of modern VLMs, but it is using it to not to create a next generation AR experiences like here, but instead to secure AR platforms. And to do that, let me take a step back and talk about the dangers of specifically augmented reality, building virtual content in the view of the user in real world. In an AR headset, you are giving a system full access to your view, and there are dangers that come with it. Your view could be abstracted, your view could be modified. So a couple of attacks that we have demonstrated this here. This work is supported by DARPA since it aims to secure augmented reality systems. Some of the attacks that we have identified and demonstrated in this case are shown on the screen there. To the left of the screen is we call this real-world obfuscation attack. This is the case of your basic visual clutter, that your AR system is adding so much information to the view of the user that the view of the user isn't as clear as it could have been. To the middle is an actual case of where things get dangerous. This is where you can abstract real world with AR information. We have demonstrated this on optical see-through and video see-through platforms both. An example that you see playing on the screen is a HoloLens app where a visual is abstracting text in the real world. And the example that's playing right now is an Android app where this little sparrow is abstracting the knife at the edge of the table. So you use a fairly large visual to block users' view of important real-world objects. To the very right is an insidious type of attack, where the type of The extent to which you modify a view of the user is fairly small. You're adding small elements to the view, but the modification to what the user gets out of the world is major. In this case, for instance, we're showing how by adding a very small visual to the screen, we are able to change the digits that the user is seeing on the clock. So these cases these are attacks. One may argue that for ubiquitously deployed AR systems, this will become real vectors of compromising users' task performance as well as safety. So what do we do about this case? Well, your user, the user who is wearing an AR headset, is seeing the real world and the virtual contents. They cannot toggle between the views. They either see the virtual contents or they don't. So at any given point in time, they're seeing text that is abstracted by this visual, for instance. It is fairly straightforward to build systems that do not have that limitation. A system is not restricted to just seeing what the user is seeing. We can have a monitoring agent that is seeing the state of the real world and the state of the user, what the user is seeing, can compare the two, and can decide whether this level of reality modification, shall we say, is potentially dangerous for the user. And we call the system guardian, that you evaluate to what extent virtual content disrupts the real world. And if you're able to do this quickly enough, then you are also able to mitigate the disruption. You have seen in one of the videos that we make content transparent, for instance, when we discover that it is blocking users' view of important objects. In signal processing, this area of comparing the state of a frame with a modified state of the frame, this belongs to the category of methods called full reference image quality assessment methods. And I'm happy to talk offline about the number of methods that we have tried in this work. We effectively discovered that classical methods just do not work here, since this level of reality modification is highly contextual. If this small white block is added anywhere else on that clock or around the scene, it wouldn't make any difference. It is specific placement in this context that is a problem. So this arguably is a job for ML, and for ML, as alluded to before, the latest and the greatest vision language models really outperform others. There's no comparison. I'm very happy to discuss this offline, but the performance is just, it's in a different class, basically. So let me talk to you about the system that we built that works on detecting specifically abstraction attacks. This work appeared in IEEE transactions on visualization and computer graphics. We presented it at the IEEE VR a couple of months ago. Here we are using VLMs, ChatGPT in this case, and an edge server to detect that important objects in the view of the user are blocked. And let me talk to you through an example of that. In this case, the user is walking around and enjoying the experience that is shown in the second image from the left. So here, the user sees a wall and some virtual content on it. What is actually in the reality is shown to the, on the frame on the very left. That behind this virtual content that the user is seeing is something that could be important. In this case, a no parking sign. So what our system does is capture both those views, and a couple of things happen there. One is that this capture of the real world, the one that is on the very left, is sent to a vision language model on the cloud, a highly performing, high-end model like GPT. And we are asking it to identify key objects, what the key objects are in the scene, in this highly contextual way. This list of key objects is returned to the edge server, where it is used later for prompting smaller models such as ground in Dyna. Then the user goes along, the user still has that experience. On the edge server, we do a couple of things. One is that we compare the real world and the augmented experience to get the mask of where virtual contents are in that capture, and that is to the very right of the screen there, so that it's just where the virtual contents are in the frame. And then we use the real world capture and the list of key objects to get the locations of the key objects within that frame. You use grounding dyno for that. This produces the mask of key objects that is to second from the right here. So now we know where the important objects are in the space. We know where the virtual contents are in the space. If you want to detect if they overlap, we're there. We have both masks. We can do this. We're done. What's very nice about this architecture is that GPT works slow on complex captures like this one. By using Edge to effectively cache GPT's high-level, highly contextual judgment, we are able to get to latencies that are much better than you would get with GPT alone. So this is a way of using, gaining a lot of latency by using Edge for output caching. Results on a data set we have curated are shown on the screen here. This is the highlight of results. More results are in the paper. A couple of things to note here is that overall the results are really good. So 90% accuracy that implies that the work is will work well in the real world. This is a performance we get with the best models. If we use lower performing models, the performance drops slightly, and that's fully to be expected. The other thing to note here is that prompting matters. How you craft prompts matters. In our system that we call VDAR, we craft prompts to focus GPT or another model on objects that are safety critical or require users' attention. If you simply ask a model to return key objects, you get results that are worse. And this is, again, fully expected. That's what happens with all LLM and VLM work currently. I also want to note latency results. These are great. This is under half a second for attack detection. This is without additional system modifications. So we can definitely improve on this with some system engineering. These methods look really, they make for very cool demos because they work really well. So we demonstrated this at a couple of industry XR conferences lately. What you're seeing here is an example on the Meta Quest where you see the shield that starts to obstruct the real world stop sign, and the shield is made transparent when the abstraction is detected. And so that is on a Quest. And an example on an Android phone is playing right now. This is where this little sparrow could be obstructing a stop sign or this knife at the edge of the table. And it is made transparent when that is detected. While doing this work, we have discovered something that's quite cool about the modern vision language models. Apparently, some of them have been trained on AR data. Who knew? And a couple of examples are on the screen there. The example to the left is where we take the capture from the app that I showed earlier, where we show the user the guidance about the trajectory of the robot. And we actually do not even tell to the models that this is an AR capture. We ask this extremely generic prompt, what is happening in this image? And apologies to those of you who cannot read it, but this is good. This is good critique. This is good information. GPT is spot on. An example to the right is where this is not our app. This is a commercial shoe try-on app. In this case, we tell GPT that this is an AR overlay, and we ask it for feedback. And note here as well that this feedback is this is the level of feedback that somebody who is fairly experienced in AR would give you about this capture. So we started digging more into this. We curated a data set of over 1,000 frames from different AR captures. We classified those captures into arguably easy, medium, and hard for the model to analyze. Easy captures are your stereotypical AR experiences. You can immediately tell that this is AR as a human user. Medium cases are where the app tries to be photorealistic, and maybe at a very quick glance, the human user would be fooled by it. But if you spend a little bit more time on it, you immediately see that things are wrong. So here the waste paper basket is floating, and the shoes cast no shadow, for instance. And the cases and then we also have identified cases that are hard, that were specifically designed to be hard. such as this case of clock modification that I showed earlier. What we have demonstrated, what we have seen in our work is that ChatGPT and Gemini, again, have clearly been trained on AR data because they excel at those tasks. Results for GPT are shown on the screen there. A generic prompt is where we do not tell it that the data is AR, and task-aware prompt is where we tell it that we are analyzing an AR experience. And you see that for easy and medium cases, the models clearly have the ability to understand them. So currently we are working on digging more into this, understanding models' abilities to analyze some specific AR artifacts, such as whether in AR, whether virtual contents are intersecting with real-world objects, or if the shadows are cast well. We're also learning how the extent to which models' judgment aligns with human judgment, and we're also learning to close this gap between human and model judgment. So overall, this is extremely promising. This means that soon enough, we will have models that are able to provide, automatically provide to us information about the quality of an AR experience, which is really exciting. So overall, VLMs are an absolutely breakthrough for semantic awareness in AR. Their abilities are so far beyond what has been available before that it's just mind-blowing. I have demonstrated a couple of applications of those abilities that are somewhat unusual. You can use them for generating semantically aware experiences, or you can use them to secure and evaluate experiences as we have to in this work. Those models are, latency is an issue for them. They're extremely computationally heavy. It is highly unlikely that you will ever run anything like that on device. So this is where edge cloud architectures are becoming extremely promising, and this is what we're demonstrating in our work. I'd like to thank the sponsors of this research, and I think I have a couple of minutes for questions if there are any.
Hi there. Quick question. Have you considered using kind of an ensemble approach to taking kind of multiple vision language models, maybe even beyond the ones that you've tried? Let's say I want to use Llama as well, and kind of have them improve collectively the judgment result that you get for perhaps what is an important object in a particular view, an AR view. Have you considered the ensemble method in that way?
So you can definitely do that. My sense is that the gain you will get from it is somewhat limited, since some models perform so much better than others that this probably isn't the key approach. You can definitely do, the work that I'm demonstrating here is all out of the box, so you can definitely do better by fine-tuning. There's no question that you can do better by fine-tuning, and as well as by several other methods. And this element of being very clear with your prompts is really important here as well, that you can imagine that for different situations, the prompts that you would craft would be different, and that will definitely help. But yeah, whatever methods you can throw at it, whatever has been shown to improve model performance here will improve the performance in these applications as well, for sure.